Thank you very much for coming to my talk, the last talk today, and I hope it will be a little bit engaging, and thank you for not going to the eBPF talk, because if you know Linux, you kind of know eBPF. There is nothing to learn from there. Okay, so my name is Ignat. I work for Cloudflare, and today I'm going to tell you about how to properly upgrade your kernel in production. So a little bit about myself. I do Linux at Cloudflare, so I'm a die-hard Linux fan. That time I'm doing this presentation from a MacBook, actually. So I also do systems, security, and performance, and I enjoy low-level programming. Linux kernel code, drivers, bootloaders, and other scary low-level stuff written in C. But before we begin, a typical show of hands question. What do you do in this case? So imagine you're just working and on your system, and suddenly you see this pop-up. So there are updates available. Install now, remind me later. Who will press install now? No one, really? Okay. My assumption is if it would be a production system, we will also be holding off, right? Yeah. So yeah, with production system, updates are kind of like a very tricky thing. You either want to delay updating or like just don't update at all. So, and that's natural, because how do we perceive software updates, right? So we as SREs don't really like software updates because they kind of bring chaos into our workflow. They create uncertainty, right? And so we kind of perceive them as monsters attacking our systems. But with regular software updates, we kind of perceive them with okay-ish monsters, right? Like they're ugly, they're annoying, but we know how to deal with them. But when it comes to a Linux kernel upgrade, this is like a game over, because this is like, it will destroy our universe, right? And there is a reason for that, because technically we know how to deal with bad software updates. So imagine you're you're on call and some of their service started segfaulting, like not very often, not continuously, but once in a day or so. Like, what do? Right? Well, you use systemd, right? And you say like, okay, just restart it and job's done. Yeah, you can move on. Yes, you will be operating in a slightly degraded mode. There will be slight impact, but it's not the end of the world, right? Whereas if your kernel crashes, your server is down. Nothing works, no observability, no monitoring, nothing, and you can't tell what's happened. You probably don't even have like screen. You have to go through out-of-band console and somehow figure it out what happened. So we don't like kernel upgrades. Nobody likes kernel upgrades. They're too risky, right? And we usually try to avoid kernel upgrades as much as possible in production systems. But there are risks, actually, by not applying the updates, and Linux kernel updates in particular. The first thing is, like, first of all, your bugs are not getting fixed. This is a specific example for the Linux kernel I collected. So every line on this graph represents a release. And I will be talking about the Linux kernel releases later, but at this point, what you have to understand, this is a bugfix release for the 5.15 branch. And these bugfix releases roughly happen every week. And this line represents number of commits, thus number of bug fixes in each release. So I took the 5.15 branch. We're using 6.1 now, but basically 5.15 has been there for longer, so you can see better statistics. So far, there have been 116 bug fix releases on the 5.15 branch, and 59, more than half of them contained over than 100 commits, so more than 100 bug fixes. 21, which is roughly 20%, is more than 200, and there are some 8 mega releases which contain 500 bug fixes. So imagine if you don't apply a bug fix upgrade, you have these lurking bugs in your system. Well, secondly, if you don't upgrade your kernel, you don't get free performance improvement. Kernel is the biggest open source project on the world, and people continuously contribute to it. And here's in a Cloudflare where we started updating our system from 5.4 kernel to 5.10. And this, we did like an A/B experiment in the system. And turns out, with 5.10, we kind of like get better memory utilization, right? We roughly save like 4.5 gigabyte of RAM per server, right? And this is all we did nothing, we just updated. And this is more thank you to some people at Facebook, now Meta. Like they were kind of improving the memory management system in the Linux kernel, and we just got it for free, right? So, and 4.5 gigabyte of RAM per server at scale, or if you pay for cloud infrastructure, you can imagine that's a big cost savings. Now let's talk about accumulating change data. This is the same data I showed you before, but now it's kind of accumulated, so the number of changes are shown from the release 0, right? And from this view, it's very easy to see the change, to calculate your change data. So imagine you wanted to upgrade from 5.15.16 to 5.15.32, and so your change delta is roughly 2,000, is exactly, basically, 2,196 commits. Now, imagine that for some reason you decide to delay your upgrade and new releases comes out, and at the time you delayed it twice, right? So for the same amount of time, and now you're on you want to upgrade to 0.48 release, but now your change delta is 5,436 commit, right? And if we make a basic assumption that number of commits is somehow proportional to risk that you're getting that your system will break due to updates. So technically, for a 2x delay, you get 2.48 more risk, right? So technically, your risk grows faster than you delay. So you may think if you delay to x, you get to x rate risk, but it's not always the case. Sometimes you get more risk by not applying like a small change delta. If you don't upgrade your kernel, security vulnerabilities are not getting fixed. This is another graph which shows how much a bugfix release has, how every bugfix release, how many security vulnerabilities get patched. So the data is not available for latest releases, but out of 113 releases for which data is available, 90% of the releases have at least one CVE patched. And 23% have more than five or more CVEs patched on our systems. So if you don't upgrade your kernel, you kind of have unpatched security vulnerabilities in your system. And having these security vulnerabilities kind of brings you with the compliance risk if you're subject to some sort of compliance. For example, Cloudflare is PCI DSS compliant, and like there is a paragraph says that technically critical or high-risk security patches updates are installed within 1 month of release, right? And it's hard to, and it's only applicable to critical system, but it's hard to negotiate Linux kernel being a non-critical system in production. Who here knows what happens to Equifax? Okay. So for the rest of you who didn't raise your hand, Equifax, it's not about the kernel upgrades, but Equifax was hacked and like data was stolen, and they had a like really long legal process. They had to pay a lot of money to affected customers, and like they lost credibility just because they didn't patch some kind of vulnerable Apache instance in production for a long time. And it also, and based on the fact that we need to patch we might need to patch the Linux kernel up to almost every 30 days. So and patching the Linux kernel requires you to reboot a system. If your server uptime is more than 30 days, most likely it's running vulnerable software and probably not compliant. Okay, so now let's talk about anti-patterns specific for Linux kernel releases. So okay, we understand we now need to upgrade the kernel. So you go to your SRE or operations team and it's like, yeah, we need to do this. And they start asking you the standardized change process, which you cannot effectively answer, right? So one of the typical ones is, okay, which things from the changelog are applicable to us? Why do you want to upgrade, right? But in the context of the Linux kernel, like, if I'm every week going to review at least 100 changes, all my team will be doing is just like rubber stamping, right? So, and remember, it's 100 is the minimum, right? And then it can be 500 and say, so there is no way you can possibly track all the changes which went to a changelog in a specific bugfix kernel release, right? Similar is if you want to upgrade to patch a security vulnerability, they kind of ask, but yeah, really, this is a CVE, but is it applicable to our system? Is it exploitable our system? And this is probably a right question to ask, but to the wrong person. So let's think of it from this perspective. Like, who is the potential attacker in your system, right? They are kind of like highly motivated to break into your system. They're like, it's their bread and butter. That's how they earn their like income, right? So to do that, they spend exclusively 24/7 to design and implement a successful exploit. So, and we've often seen cases in history where like attackers were so smart, they kind of like were able to properly chain 5 minor vulnerabilities to get an exploit. Whereas if you take each vulnerability and analyze it, it's kind of like minor, but somehow successfully chaining them, they're able to get an exploit into production system. Yeah, so this is the attacker, right? So attacker actually can tell us if our systems is vulnerable to the CVE. But we're not asking that question to an attacker. We don't know who they are. Like, we ask this question for like a Linux engineer or a security patch reviewer who is different, who is highly motivated to go home on time. They probably need to review several patches a day, so they cannot spend like as much time as the attacker trying to think of a successful exploit, and probably has some other competing priorities like compliance, writing secure code, secure design reviews, etc. So we're asking that person, right? So do you really expect to get like a meaningful answer to that question? Common strategy in the production releases is soaking. Okay, it's fine. We need to upgrade it, but let's just soak it for 1 month, some kind of in canary to ensure it's stable, right? But why is this a bad approach? We can go back to accumulating change delta. So the more we soak, the more we delay our upgrades, right? We also come back to the security question. So the more we soak and not pushing it to the rest of the production, the more we run the production with known security vulnerabilities which can be exploited. And probably if we do it more than 30 days, we're also risking the compliance as well. So let's step back and think, what is, like, if you want to soak something, like, what does it actually mean? It kind of means, like, we don't know what we're looking for, right? When you deploy a service, you kind of have these good metrics saying, like, oh, how many requests per second does it do? How many requests succeed? How many? You have, like, these successful metrics, but probably something can be done with the kernel as well based on the specific workload. Or you can even collect metrics from your workloads to see if they perform as good on the new kernel as previously. This probably also means we don't know our workload. So my team oftentimes get questions, if you upgrade the kernel, will my service break? It's like, how should I answer it? Like, I don't know what does the service do. Like, some services are CPU bound, some services really require some extra networking features, some services require faster I/O subsystems. So we cannot answer this question, actually. So it's up to probably the service owner to better understand that workload and translate it, like what kind of the performance they should expect for that specific workload from the kernel. And probably it's lack of sufficient pre-production kernel testing. So kernel can also be tested with unit tests. You can have like some integration tests and performance tests. But usually in our production system, we engineers do that for their services, but they don't kind of like do the testing of the kernel interfaces. And our teams, like the kernel teams, they cannot do these tests because we don't know what to test actually, what services need. Finally, is like, I often see this like with newcomers, it's like, kernel is just too critical. Let's just have more approvals before we deploy. So like, if like a regular release requires 1 approval, a kernel will like require 3 approvals, right? And again, this is natural because we like the perception of the kernel is just like it's that monster, right? But what if I told you that kernel deploys are inherently safer than any other software in production? So on the example of Cloudflare, my colleague already showed you this map. This is a Cloudflare network today. Each dot is a data center with multiple of servers. And we have, obviously, we cannot deploy stuff manually, so we have automated software deploys, right? So how does from a high-level perspective, a regular software deploy works? So an engineering team like pushes new code to our code repository. So they upgrade like some package in the repository. Then eventually that package gets propagated to all the servers. And like if there is a service running that code, it can restart. It just sees there's a new code is available and restarts itself, right? It can be graceful or non-graceful restart, but it doesn't matter. And this thing happens really, really quickly. So the problem is that if the code is bad, it can propagate to all this network within minutes. And unfortunately, actually, Cloudflare learned it the hard way. So we had some severe outages where a bad code propagated like in minutes to the whole network, and we had like a global outage. So some of the blog posts, public blog posts about them are in the links. But if you compare it to the kernel, the biggest advantage or disadvantage, but the feature of upgrading Linux kernel, you require a reboot, right? And I hope nobody is silly enough to reboot the whole network at the same time. So we do it gradually, one by one. We cannot put all servers immediately out of production to upgrade the kernel. And rebooting a server is kind of like a complicated workflow. So we need to drain the traffic from the server, disable it, put it out of production, actually reboot. If you deal with real hardware, you know, like servers are not booting fast these days for some reason. Then when it boots, we wait for it to be reconfigured. Then we run some simple acceptance tests before we can put it back into production. And then we put it back into production. And again, as I said, we do it one by one or in small batches, depending on the capacity we have in data center to make it non-impactful for the traffic vessel. So if you build a sane kernel reboot system, your kernel upgrades are inherently slow-paced with gradual rollout and minimal impact. And if things go wrong, you will notice it like on the third server, and you can like press the big red stop button. So with minimal impact. Are you convinced? Who is now going to upgrade the kernel in production? Oh, yeah, good, good. One thing is interesting when talking to people about kernel releases, they don't actually understand that not every kernel release is created equal. There are bug fixes releases, feature releases, and so on. And this is like I will try to demystify it now. So kernel release is designated by a number, a dot, another number, a dot, and a number, right? So, for example, 515.32, right? Who here is familiar with semantic versioning? So, take away from this talk, this is not a semantic versioning system. This is the biggest mistake people make who are familiar with semantic versioning. Kernel releases do not follow semantic versioning. So they have a major version, which is designated by first 2 digit, and they have, so it's not major, minor, like in semantic versioning, and they have bugs and security fixes, right? And incrementing this last number will never get you new features or major subsystem rewrites. It's only bugs and security fixes. So this is why if you're upgrading with just like when you increment the last version, you kind of like never get a breaking feature in your kernel. So this is why they're usually safe to apply. So how does kernel releases usually work? So the main code is still in this, is held in the current, well, we call it bleeding edge code, is stored in this Git repository which is managed by what we call the benevolent dictator with a single right to approve changes. And actually development for various subsystems happens in different feature branches, right? So like, let's say we have a branch with drivers, a branch for memory management, branch for networking, and eventually at some point when the branch reaches like some kind of feature completeness, Linus merges pulls from these branches into what we call the mainline branch. Then when Linus deems that a kernel is stable enough to make a major release, he branches it out a stable branch. So we have like a stable branch for 5.10, 5.11, 5.12. And this happens roughly every 9 to 10 weeks. Well, and then each branch eventually creates a bugfix release called like 5.11.1. This is the first bugs released on the stable branch 5.1. So how do actually bugs propagate to like bugfix releases? So if you're a developer and you discover a bug and you want to submit a patch to it, you're not actually submitting it to these release branches. The rule is you almost always submit it to a respectful memory, to the respective feature development, right? So if your bug is in the drivers, you submit it to the drivers tree. If your bug in net, you submit it to the net tree. So eventually that bug fix through to next pull by Linus propagates into the mainline branch. So this is basically, this process is to ensure that if you discover the bug in the stable kernel, the fix is also available in the bleeding edge kernel. But stable branches are never pulling from the mainline branch. Instead, these commits, these bug fixes are specially marked, so these stable branches are cherry-picking these bug fix commits onto the stable branch. And then when enough bug fixes accumulated, they do a new like bug fix release, which happens roughly every week, usually on Wednesdays, depending on your time zone, of course. So, yeah. So a new major stable kernel version is released every 9 to 10 weeks, and you may say, well, is it tested enough? Well, so developers only have 2 weeks for development of this called like a merge window. So developers only have 2 weeks of merge window for actually developing, and then 7 weeks for bug fixing. So even before the stable branch was released, that stable branch undergoes testing for 7 weeks out of 9 or 10. The one thing which you should definitely take away from this talk, leftmost version number means nothing. So as Linus usually puts it, I usually increment it when I run out of fingers on my hands and toes, but sometimes you get 5.21 and then he increments it to 6, but somehow you get 4.19 19 and you increment it to 5. So somehow his fingers are different each time, but whatever, it's up to his decision. And this is the biggest mistake when SRE made, when you come say like, oh, we're upgrading to a new major kernel, like they're kind of okay if you upgrade from 4.19 to 4.20, but if you tell them, no, we're upgrading to 4.20 to 5.0, so like, oh, that's probably a super release and we need to test it. No, it's the same thing. And and bug fix or patch releases are released around once a week, and they're denoted by rightmost version number. All the bug fixes are usually cherry-picked from the main Linux branch, and there's no new features, and therefore regressions are quite rare. And they also contain critical security patches. And by the sheer volume of commits and bug fixes, there is most likely there is definitely something which is applicable to your system, either a security or a bug fix. So you almost always want to apply them. So every week you should try to upgrade your kernel to the next bug fix release. So what about like major stable releases? It's still like when we actually upgrade the major version, we do want to do some extensive testing because we get new features, subsystem rewrites, right? And the problem is that the stable release branch is actually active. Active means bug fixes are being backported to it around only 2 or 3 months. And after that, it's declared end of life and abandoned. And by the time, like 2 to 3 months, a new major stable version should be available, so you are kind of encouraged to move. But it's understandable that not everyone has the capacity to actually evaluate a new major kernel version every 2 to 3 months. So for this, the Linux kernel project also designates some releases as long-term support. And this means that this specific release with bugs and security features are backported for at least 2 years. And it's usually the last stable release of the year. So long-term kernel released every year, and it receives at least 2 years of bug fixes support. So basically, you have enough time for more rigid evaluation of the next release. So you can use it for a year, and at the end of the year, you can start slowly evaluating the next long-term release, and by still getting the bug fixes in your current long-term release. If you're interested, it's actually written on the kernel.org website, including the major versions, so with a link to Linus fingers thing, so go and check it out. Okay, so safe and easy production kernel upgrades. What should we do? Based on all I said, well, first, don't create a dedicated process for the Linux kernel. If you have a clearly well-defined release process for any software, just use it. Because kernel upgrades are usually less risky than any other software, and a simple stage rollout is usually just enough. And you have to remember that kernel upgrades are usually slow-paced, are naturally slow-paced because it requires you reboot, so it leaves you a lot of headroom to abort or deploy if things work wrong, right? So it will not quickly propagate to all of your production. Do avoid justifying a bug fix kernel upgrades. Just remove that. Like, there is no justification every week you should consider upgrading. Because, you should try to release it with no question asked, because it only contains bug fixes and security patches, and there are so many of them, and so most likely some are always applicable to your system. And you will just save time building a really good system of continuously deploying the kernel upgrades versus like arguing should we apply it or not. Regressions are quite uncommon. Like in Cloudflare, we now trying to do it almost on a weekly basis, and we rarely see any problems with the bug fix upgrade. And try to minimize the canary soak times. Like try to use metrics-driven approach to see if a kernel release works well or not. So define some kind of metrics for either your server or critical services and monitor them to see if the kernel release didn't create any impact. Yeah, if it is too costly to evaluate a new major kernel version, stay on the long-term branch. And actually, if you use a kernel from a popular Linux distributions like Red Hat, Ubuntu, they usually just do exactly that. Their default kernels somehow stay on the Linux kernel long-term branches, so you kind of like upgrade them without too much risk. So you get at least 2 years of bug fixes, security patches. But the advice is don't wait for all the 2 years, right? Because it will be abandoned eventually. Start evaluating the next long-term release early, like after 1 year when it's available. You will always get more features. You usually get better performance and resource utilization. Like kernel continuously improves and like it gets better and better. And you will be, by upgrading more often, you will be accumulating less change delta. Do consider to implement or improve, if you already have it, pre-production testing for major version validation. So basically it means try to understand your workload. Kernel is a huge collection of interfaces and subsystems. You're probably not using all of them. If you even have a regression in some rarely used subsystem, which is not applicable to your workload, it's okay, right? Try to understand what exactly you use in the kernel and write tests for it, like which exercise the kernel subsystem required for your log. If it's I/O performance exercise, there are like benchmarks for disks and everything. If it's some CPU or scheduling, so real-time capabilities, verify them. And do make metrics-driven decisions and not time-based decisions. So don't try to soak it. Instead of try to design a system where you look at the metrics and they give you an immediate answer like this is good or not good. With that, metrics monitoring and deploy automation can help with human risk perception. Use data-driven decision if the deploy looks good. And when you have data, it provides you with quick and early signals about regressions and can save the engineering time and debugging cycle. And debugging the Linux kernel is quite hard and time-consuming, so it's very bad to receive false positives that people usually think it's a kernel problem, but in our case, 99% turns out it's kind of like a service problem eventually. And my colleague here just recently touched on automation. And automation, autonomous automation, I would say, really helps here. Because when you onboard, we've seen that when you onboard new people in operations and SRE team, again, they have this real biased perception of kernel being more risky. And we've seen previously that if they're responsible for rolling out a new kernel to production, they try to avoid it and do I need more approvals here? Or that. If you have the process automated, you kind of remove this human and operator bias from the process, and it kind of works well in the end. This is basically what I wanted to say for today. So. Yep, Linux kernel upgrades are not more risky than any other software. You do need to patch early and patch often. Your kernel bug fix releases should be applied with no question asked, and understanding your workload metrics, monitoring, and automation will allow your system to stay patched and secure. Thank you very much, and I'm now happy to answer the questions.